My name is Rhys Bowley. I'm one of the product managers. I work at National Instruments. You probably hear my accent, so I'm from the UK, but I now live where our headquarters is in Austin, Texas, so just one state over. And what I do there is I'm technically in marketing, and that means my job has two sides. Now, one side is the promotion of the tools that we make, and the tools are the hardware and software that's in front of you. But the other side of things is actually informing the roadmap for the new tools and the new software that we'll make. So I meet with people like you, people who work in the communications industry and in academia, research and teaching. I come to ask, what it is that you want, what's going to happen in the future, and what will you need in the future, and I take that back to R&D and put it into the new products. So if anyone has feedback, I'm very, very open to it. So I'll do a little bit of background, and then what I'm going to do is I've changed up my normal presentation style a little bit because I want to try and make this like 99% hands-on. So I've got a few slides that I'm going to tear through at a really fast pace, and then we'll get onto this. So a little bit of introduction then. So I have a bachelor's and a master's in wireless communications from Cardiff University, where they only do two majors in ECE. One is in wireless and one is in power. So Dr. Anna would have liked that if I should have told her when she was around. Wales is on the side of England. Unfortunately, most of my American colleagues ask if I'm from London. The UK is a little bit bigger than that, and you can see Cardiff down there on the map. Now, interestingly, that particular place is where the first ever wireless communication signal was sent in the world. A little place called Lavenock Point by an Italian guy called Marconi. So that's Lavenock Point, that dirty rock up there. That's about 12 miles from where I live, or where my parents still live. And Marconi was an Italian professor and inventor, and he started inventing those spark gap radios, realized that he was making a transmission over the airwaves, even though he couldn't see it or explain it to begin with. And he approached the Italian military in order to get funding for his idea. They laughed him out of the country. They actually promoted bad press about him and wrote fake news articles saying that he was a madman and should be avoided. So he came over to the UK, and the English army said, the idea that we could talk to our soldiers from 20 miles away, that sounds quite useful. World War I was just on the horizon, but nobody would believe his invention was real. And we often get this problem in communications, right? Everybody thinks that we're like voodoo magic, and that these devices are black boxes where magic happens inside. But it's not that complicated, I promise, as we all know. So what they did is they took him to this cliff, and they sent the receiver out to an island 3 miles out in the sea, because that was the only way the military would believe that there wasn't a hidden cable under the ground. And they sent the first ever wireless voice transmission that way. The only thing which commemorates the first ever wireless communication in the world is a dirty, stained little plaque on the side of a church at Lavenock Point, which is still there today. So a little bit of history for you. Now, I get to work mostly in teaching, and Professor Ramiro Jordan and Michael here, they teach with the National Instruments USRP radios and LabVIEW. And another one of our speakers, Fabrizio Brunelli, teaches with those tools as well. But I want to just impress upon you, because this may be a way in which your careers go, that the efforts of teaching and research are maybe not so different, especially in this area. And the reason they're not so different is because you're just trying to prototype and discover the unknown. Now, for a student, that's like really basic stuff, right? They're trying to discover calculus. But for the PhD researcher, you're trying to discover something that's unknown to human knowledge. The only difference is the scale, right? But the types of problem you come up against when you're trying to discover something you don't know about are exactly the same. So that's why we use the same hardware and the software throughout both. And it applies everywhere. So let me rip through this. We all know 5G and the classic problem statements around it. The reason that we work with these radios, if I was to take a very candid and frank way of explaining this, is because now prototyping is absolutely necessary if you want to make any progress on the world stage. So 5, maybe longer, maybe 7 years ago, you could go to IEEE conferences and you could present just a paper with a theory for a new network architecture. Now, that's not good enough. Everybody who is on the world stage has a working prototype. And you may have seen with release for the 5G round, release 15 now has been slated. Release 14 is done. Release 15 is going to drop in 2 drops. One this December, the next one with the full 5G control layer in, I think, June, July next year. And the timelines are being brought forward very aggressively. And now we're stuck with OFDMA. I have my own problems with that. But anyway, hopefully new waveforms will come in the later releases. But what you see is that when people are making submissions and contributions to the 3GPP standards and the IEEE standards, is that those with a working prototype get taken up, even if the other idea is a better idea, because time to market now is so important and we're rushing towards these insane deadlines that we're not even sure we can meet. So if somebody has a working system, it's so much more valuable. So that's the importance of prototyping. Now, we do prototyping at National Instruments in 4 main areas within 5G, but these devices get used in radar, in sonar, in astronomy, all different kinds of fields. Because they're a software-defined radio, you can program them to do whatever you want. But these are the main vectors, as we call them, columns, pillars of our 5G work. So the first one up is massive MIMO, then advanced network architectures. This is very closely related to things like cloud-based RAN that we've talked about this week. Multi-rat and basically better waveforms, so things like Gerhardt FET devices, GFDM, LoRa waveform, things like that, and then millimeter wave, so higher spectrum, channel sounding, all that kind of thing. What I want to do just before we use the radios is give you a little impression about who uses these radios and what they use them for. So let's dive in. So massive MIMO, we're all familiar with massive MIMO, right? We can take multiple antennas and start to beamform in order to serve multiple users on the same frequency. You get much higher spectral frequency efficiency. You get much higher transmit power efficiency. So there's a lot of interesting work going on here with these radios at a number of different universities and a couple of big names out in industry. I want to show you a couple of the examples. So these two are 2 customers of ours, and you'll recognize these are those radios you have in front of you and some down here. This is the base station all in the rack, and these are the user equipment. And then this is Facebook's base station and their user equipment that they actually have on. Can you see it's on wheels? It's automated, so they can drive the user equipment around to different places. Now these 2 guys were competing for a long time, but they're actually in very different fields. So what Facebook are doing with Project Aries in the Facebook lab is actually trying to use millimeter wave up at even 90, 91 gigahertz, and they're trying to use massive MIMO in order to push the signal further, because you can focus the beam, like a bulb versus a spotlight. You can make the energy actually travel further. And they're trying to do that from a rural mobile broadband point of view. So they want to be able to begin with fixed point access to rural areas. And you've seen the previous Facebook lab projects around their internet access in India. They currently have a couple of balloons, helium balloons up over Peru for disaster relief broadband internet. So it's this similar kind of idea, being able to deploy a mobile broadband network without the need for putting in physical infrastructure. And then Bristol, coming from a different point of view, they were actually trying to drive spectral efficiency. So this is part of a city-funded project in the city of Bristol in the UK, where they are trying to realize the Internet of Things and all of those billions of connected devices. Now there's nowhere near enough spectrum available with our current technology under 6 gigahertz in order to connect maybe 1 million devices in Bristol. on top of the existing mobile infrastructure. So what they're looking at doing is using massive MIMO in order to spatially multiplex. And then these guys started chasing each other. So we got a call from Bristol. They called us up and they said, hey, we just hit 70 megabits a second. 70 bits per second per hertz is the correct measurement for our spectral efficiency. It's a new world record. Facebook said, no, we're going to have you. 3 weeks later, Facebook called. They said, we did 71. So Bristol went back to the drawing board. They expanded their code base to handle 22 users at once with 1 second position updates. So not something you could use for like a high-speed train or a car, but for someone walking around. And they managed to make 146 bits per second per hertz, which is, I believe, still 18 months later. That's still the world record. We'll see who comes and calls us back in the future. So this is an overview of the people who worked on the Bristol system. I can give you these slides afterwards and a bit more detail. So this was their system architecture. Now you have one radio in front of you connected via PCI to a laptop or PCI Express. They had 128 antennas on their base station maximum. They made an antenna design for 100 antennas, which allowed them to do either 4 by 25 or 10 by 10 configurations. And what they did is they took all of those USRPs back to PCI switch boxes, which went back to a National Instruments PXI chassis, where there was a Windows host controller. So all of this was hosted by Windows 7. Windows was making the high-level and high-layer decision-making, but all of that physical and Mac layer stuff was being pushed down to the FPGAs that are in these radios in order to do that inline fast processing and be able to meet the timing requirements. Okay, so we'll switch to slightly different aspects. So this was on our NI Week keynote stage a couple of years ago. So this was what Samsung did with FD MIMO. Is anyone familiar with FD MIMO? Okay, so exactly, yeah. And being able to do full duplex MIMOs, going to not just take that 140 bits per hertz per second, but that could increase that. If we can go full duplex over the channels instead of TDD, FDD, all this kind of thing, then we could push that 140 megabits per second to 400 megabits per second per hertz. And that would be an absolutely insane number. And then as well, they were doing a bit of full dimension as well, whereby normally we talk about MIMO, we put all the antennas in a row. That only gives you spatial multiplexing in one plane, X and Y. But if you were to put the antennas into a 3D grid, then you can start to spatially multiplex up and down as well. So we've gone from focusing these triangle-shaped beams to now focusing spotlight beams. And that's really good if you want to service like an environment like a stadium, or maybe you have an apartment block of flats. Now you can target a certain flat within that apartment block. Apartment flat. I'm trying to translate for you guys. Okay, so this is just a splash of looking at what Intel did with their Blade servers in their cloud-based networking. So all of this was built into one rack. You guys might have seen it at GlobeCom and a couple of other conferences, ICC as well. So this is I think it was 64 antenna, 8x8, massive MIMO base station, up to the PXI chassis, remember, getting all of that data together and making the high-level decisions. And then up here, what you see are the Intel Blade servers, and just above, you see another 4 USRP Rios, just like the ones you got. Those are the user equipment. And whilst this is all in one rack, the idea was that all of this cloud-based infrastructure could be anywhere in the world. This could run on Amazon servers, could run on Intel servers that could be in an entirely different continent. So that gives you a huge amount of flexibility as to what network topology you want to push down, and that's what then really allows for slicing. Slicing won't be possible without some kind of software-defined nature within the upper layers of the stack. And then lastly, we'll jump straight into some millimeter wave stuff. So these USRPs go up to these ones are 2.2 gigahertz actually. These are some of the older models. we have USRPs that go 10 megahertz up to 6 gigahertz. But if you want, we have hardware as well that goes into millimeter wave for things like high accuracy measurements in channel sounding. But you can also use these USRPs as the intermediate frequency within your super het design, and then you can externally put a millimeter wave head on the front of that. So we worked with NYU Poly and Nokia on 2 different kinds of case studies. So the first one up, this is Dr. Ted Rappaport from NYU Poly, and he used to be at UT Austin actually, right next door to us, before he moved there. Now Ted's always been into the millimeter wave side of things, and up until very recently, all of the 3GPP standards were being centered around, how to say it politically correctly, around a millimeter wave channel model which was almost entirely theoretical and based on how millimeter wave CW sine waves interact with an environment. Nobody had ever taken a complex wave like a CDMA wave, pushed it up to millimeter wave, and then seen how a channel or a room or an environment reacts. Ted was one of the first to publish any data on how real-world communication signals react at millimeter waves, and it turns out it's wildly different to how a sine wave interacts with the environment. So his environment was New York City. That was his playground, and he set up, you see these motorized stages with a millimeter wave head on top. Out the back it goes to the PXI chassis, and a horn antenna on the front for that directionality. And what he did is he set them up around the city, and they were automated, so they could turn around and do channel sounding within New York City. And the results he got went into the 3GPP standard, and now almost all of us within 3GPP are working off Ted's channel models, and have been for a couple of years now. And then lastly, Nokia were again, like the massive MIMO side of things, they were in millimeter wave as well, but they had a very different interest. So Nokia have come from being the world's foremost handset provider. Most of us are probably old enough to have remembered owning, 3210, the indestructible phone that lasted a week on battery. But now what they're looking to do is more on the base station side, more on the service providing side, and what they were working towards was up at millimeter wave you can facilitate channel bandwidths that are absolutely huge compared to sub 6 gigahertz. So instead of your typical LTE channel bands at 20 megahertz, 40, maybe if we look at 802.11 you have 160, and now people are talking about 200 megahertz channels. At millimeter wave, just instantly you can have a 1 gigahertz channel bandwidth or a 2 gigahertz channel bandwidth very easily. People are now starting to talk about 3 gigahertz channels, and what that allows you to do is push the data rate insanely high. Now, I don't know what we're going to use this data rate for on our mobile phones. You can download a full 4K Ultra HD video in 10 seconds. But then again, when we made 3G and CDMA became popular, YouTube didn't even exist, let alone YouTube on our phones. And I've already used YouTube on my phone a couple of times today, looking things up, so I promise I was paying attention. So anyway, all of this is the type of prototyping that people do with these radios. So let me give you a little bit of background then, just about why the radios exist in the first place. So this is traditional radio frequency hardware. Signal analyzers, signal generators, VNAs, VSGs, all this kind of thing. A lot of it is instrument grade, meaning it is incredibly accurate, very highly calibrated, needs constant calibration for the numbers to be valid. It's large, it's bulky, it's not mobile, and it's definitely not user-friendly. If you can program these instruments, you tend to need to get the command set book out in order to know how to program them. But a lot of them come with absolutely no programmability at all. So from a prototyping point of view, if you want to prove your algorithm, it's going to take you some time and a huge amount of money in order to set up a system like an LTE stack trying to use RFSAs and RFSGs and things like that. So what do we use instead? Well, over the last, I would say, about 10 years now, we've had the opportunity to work with software-defined radio. So 20 years ago, this technology is so new that 20 years ago, the only software-defined radios that were really valid and in existence belonged to the military. They were the size of the back of a truck, and they cost $2 million upwards a piece. And they were definitely not user-friendly, mobile, anything like that. About 10 years ago, we got the first USRP model, and then in about 2010, you started to see things like the N210 that some of us have mentioned already in previous sessions. So what is a software-defined radio? Well, many of you will be familiar. Just out of interest, who's used one before? Maybe a third of the room? Okay, cool. So you take all of the stuff that you would have done for your particular communications algorithm or stack, and instead of doing it in hardware, you push it into software, and you give a generic RF front end that just pumps back and forth IQ data. And that's great because that keeps the actual RF side of things very low cost. And we put all of the rest of the stuff is now very flexible on these computation targets that run software. So great, right? Problem solved. Not quite, because what you've done is you've now lowered the cost problem, but you've caused yourself a complexity problem. So where you could get an adder, a multiplier, a voltage control oscillator, and solder them together, or have somebody solder them together for you on surface mount, now you need to program all that functionality. Some of it is harder to describe in programming than it is to describe in hardware. And not only that, you're now working with things like CPUs, FPGAs, communication buses. That means you've got to know how to write your own driver. You've probably got to start your algorithm in something like MATLAB or another .m syntax. You're going to have to simulate that, so maybe you hop over into a simulation environment. Then you have to take all of this from that language and translate it, maybe to C if you're lucky, but probably more likely to VHDL to run on the FPGA, maybe even machine level code depending on what your hardware is and what you've put together. And then you have to debug and deploy all of this. Suddenly, it just became unreasonable to try and use software-defined radio when your background is as a communications person, not as a computer scientist. So what do we do? Well, you know, this is a complexity problem. It's also a time problem, which is important for you when you're trying to deliver on deadlines. It's important for industry when they're trying to get to market as well. So we described that algorithm development stage. Then you have to go into the mapping stage. And if you come up against problems in the mapping stage you can't come around, you have to go back to the algorithm and you have to start trying to problem solve here before you can get to the next stage again and prove out whether you actually did. And it takes ages to go back and forth this process. So wouldn't it be cool if there was one environment that covered it all? You could do the algorithm, you could do the system mapping, and then you could deploy it to a working prototype without ever having to learn a low-level programming language or having to step outside of that one environment, so you don't have this back and forth process. And lo and behold, as you guys have probably guessed, for us at National Instruments, that whole environment, that is LabVIEW. So that's what we'll do. I'll show you how to design an algorithm, show you how to deploy it, and then I'll show you how to get it working over the airwaves. So, without further ado, let's actually use the radios. Now, what I'll do is I'll try and run the class from the front here, and everyone can follow along. Some of you will be new to LabVIEW, some of you will be new to software-defined radio, and so forth. So please ask questions, make this interactive. Don't make me wear out my voice the whole time. And we'll walk through and I'll show you what to do at each step. Now what we're going to do is just take the hardware and the software for a test drive. I'm not trying to teach you how to use LabVIEW. I'm not trying to teach you what software-defined radio is. I am definitely not trying to teach you how to implement LTE or what is an LTE stack or anything like that. Remember, I got my master's, you guys got your PhDs, so we got to respect that. But what I will do is take this thing on a little test drive for you, and what you should find is that you already have LabVIEW Communications open on all of these laptops. So that is our design environment. Now, a little word about LabVIEW Communications is that before today, had anyone not ever heard of LabVIEW? One or two? Okay. So, we use LabVIEW at National Instruments in every span of engineering, from monitoring bridges to Formula One race cars. I just put LabVIEW in space. That was really good fun. We do everything with it. But LabVIEW Communications is a special version of LabVIEW that we built just for communications guys. And what you find is there's a whole bunch of inbuilt IP and things that make building a communication system just a whole lot easier compared to trying to use normal LabVIEW. You could use normal LabVIEW, that would be fine, but it would be a bit like trying to use C with no toolkits, for example, or something like that. So does everyone see this screen? Any problems? Okay, so this is the welcome. Oh, actually, this says learning. Yours might say projects. You see, we've got these tabs at the top here. So there's a welcome screen. There are the projects. So a big thing about LabVIEW is we're trying to make it easy for you, without a computer science background, to be able to start working on prototypes. So this project, these are all fully working, fully documented example projects that you can take, either use them as a stepping stone, use them to prove an idea, tear them apart, make them your own, all that kind of thing. We'll talk about the hardware later. I've actually not got any hardware connected yet. And then there's this learning section. So LabVIEW is a programming language, and like any programming language, there is a learning curve. Now, I hope that you'll find it's nowhere near as tough as a text-based traditional language, but let's see. Depends on what your preference is. And within the learning section, you see there's learn and there's examples. Now, examples are example code. They're complete, they're ready to run. The learning section is what we'll be using today. These are lessons, and a little wizard comes up. It's nowhere near as annoying as Clippy, if you guys remember the paperclip from Microsoft Word. And it walks you through exactly how to use the environment for a particular task. For now, though, navigate back to projects. And we're going to dive right in the deep end. So you guys here in the front row, you are all my Eno-B. You are my base stations. And everyone at the back, you're going to be user equipment. And I'm going to show you just how quickly we can get an LTE stack running using the built-in ones here. So if you scroll down on projects, you'll see application frameworks. So these are things that you can add on to LabVIEW Communications. Now, you only have two that I've installed. There's a third one now as well. So we have the 802.11 or Wi-Fi application framework, LTE. We've got one for massive MIMO. And we're about to finish our one for millimeter wave projects as well. So what we're going to do is use this one. You see on the bottom left, LTE design, and we're going to do a 40 megahertz channel. Don't use the 120, there is a 161 as well. The USRPs that you have are rated for 40 megahertz. So when you click that, it says, do you want to create? And you can just say yes, create. And what that's going to do now is it's going to go back in behind the scenes and create all of the code that you need for this project. So we'll let that get going. I'm on battery power here as well, as you can see. It'll take me just a little bit longer than you. So you can see now the environment starting to open up. And a piece of code is actually open and ready to begin with. So let me walk you through this. Over on the left-hand side, this is our project. These are all the files that are together that make our project up. Here, this is one of those files, one of those pieces of code that's open. And underneath here, we have errors and warnings. And luckily, there's no errors and warnings. Does anyone else see an error? Yes, I win, for now. So go ahead and close errors and warning using that little X. And it'll disappear. We get a bit more screen space. Screen space is important here. These laptops haven't got a very high resolution, so we'll try to keep as much screen space as possible. So let me just show you now what's in here. What you can see is there's some top level files. This, like you know when you're programming C, you define main as your main routine. These are like main up at the top. And where you find all the subroutines are down in common, and there's some more in LTE here as well. So some of them are just common USRP functions, and some of them are very specific to the LTE stack. Now this stack is not complete. It's the entire physical layer, and it's part of the Mac layer on top as well, but just what's necessary. To describe what we do with this hardware, National Instruments started 40 years ago as a test and measurement company. We're all about signals. So when mobile communications came along, we were very well suited to the physical layer. And we have some Mac layer and upper layer stuff as well. We interface LabVIEW communications with NS3 and other programs like that. But typically what we do is very focused on the physical layer. So here what you see is there's a whole bunch of FPGA code. Now the FPGA is inside your radio. Ah, look at my Diddy radio here. This is a different model. These are some of the ones that we teach with. Much lower cost, tiny FPGA inside here. You guys have got a Xilinx Vertex 7, which is why each of your radios is so loud, because that FPGA is a massive source of heat. If you think about it, actually, an FPGA is a set of logic gates. Once they're all configured, they're all open. An FPGA is a giant short circuit. But that's why they're creating so much noise. So your FPGA is inside here. We will put some of the code on that FPGA to run on the device, and some code is going to run here on the host. That's what we call the PC or the laptop. And there you see, if we expand this folder, there's all of the LTE code that's going to run up here on the laptop. Now, you can use these radios with LabVIEW, or very quickly, in 5 minutes, you can flip the firmware, and you can go and use them with GNU Radio, which is C and Python programming, open source. To describe the different ways in which we typically do things, at National Instruments, we have a lot of FPGA history. So we put as much code on the FPGA as possible. And we do as little on the laptop as possible, because typically the laptop is the bottleneck, or the PC. With GNU Radio, the powerhouse of GNU Radio really is the C programming, and then the Python links the C modules. So they do as much C programming on the CPU, and they do a very little VHDL on the FPGA. So their approach is the other way around. Both approaches work just as well as each other, depends on, again, what your background is. So let me close all this down, neaten this up a little bit so we can see a little easier. Now what has opened up is the LTE host downlink piece of code, and this is a complete transmit, receive, loop back piece of code. We don't want to do that. That's just transmitting and receiving on the same device. Let's prove that this works over the airwaves for real, and I'm taking a bit of a risk here. So right now I'm going to play the, no, not yet. I'll play that role in just a minute. Using the little X at the top, close that piece of code. We don't want that. Loop back. Guys in the front here, you're my base stations. Can you please go to this piece of code, double click it, and it'll take just a minute to open. This is your base station. You might see this arrow is not yet green. It'll turn green after 10, 20 seconds. That means the code is compiled and is ready to run. What you need to do is just a couple of things. Over on the right-hand side of the code here, it says Rio 0. And it says clock source is internal, so it's going to use its own reference clock. That's good news. And then what you can do is just press the run button. I know, well, why did I do that? I have no hardware connected. So I'm going to come back now and just take a look. Cool. So over on the right-hand side of that code, there's this FPGA ready. Now what that means is that we have fully deployed to the FPGA, and the FPGA is ready to go. You should have a blue box in there. Does anyone not have the blue box? You got it? Cool. Right, now that the FPGA is deployed, we're ready to run the base station. So what I want you guys to do is come over here to the transmitter. You see this on button, I want you to turn the transmitter on. Do you see the graph populate underneath? Let's see. Right, you'll get a warning message because these laptops have brand new version of Windows on. So just say yes, just allow it to communicate over the network, public and private. Looks like everyone's running. UEs, at the same time, can you close the DL code and can you go to, is it LTE host UE? Can you double click that one and open that piece of code? And then when the arrow turns green, press the green arrow and go to see if yours says FPGA ready. This looks good. This looks good. Okay, base station guys, you are running the transmission of an LTE stack. Now turn that off if you can on that code. And let me see. I might have got the steps the wrong way around. I'm going to play the role of the FCC now. So these guys go to 2.2 gigahertz. So how am I going to work this? 1.7 gigahertz. That's what you guys are going to be. What you should find is a frequency control. You might have to go over to, yeah. Okay, so you want to change that to 1.2G. 1.8? 1.8 gigahertz, 1.9, and you guys can leave it at 2. You get 2. I'll collect the submission fees for that after. Can we do the same? So 1.7, 1.8, 1.9, and then you guys can both go on channel 2. You'll both receive off this one base station. Okay, now try running your transmitter. Excellent. So base stations, now you're transmitting just the downlink side of an LTE stack, but let's get some uplink going as well. So can you turn on your receiver and tell me what you see on that graph? Okay, that's good. Do you see a bunch of mess? Oh yeah, please run the frequency. What is it? Okay. Let me take a look at mine. So if you go for 0.75, 0.85, 0.95, and then 2.05. Yeah. So can you see that you have this receive frequency? So we're doing FDD, right? So let's change that. Just put it 0.05 of a gigahertz above your transmit frequency. And you'll have to turn the transmitter off to get that frequency to apply and then turn it back on. Sorry, the receiver, I mean.
The receiver only?
Yeah, just a receiver. And then if you turn it off, back on. Cool. So you should see very little. There's a little bit of noise in there, that's interesting. There's a couple of spikes. This is good. This is good. Oh, a couple of spikes there. I wonder what that is. All right, we're good to go. So guys, are all your FPGAs ready? Excellent. And your frequencies for your receive is 1.7, 1.8, 1.9, 2.0, right? So can you please press on for the receiver on the left-hand side? Oh, sorry. Yeah, sorry, I've done that wrong, haven't I? Sorry, the receiver's on the right-hand side. So you can... Okay, it's kind of messy. It's not bad. You guys have got something sort of... There's a bit of a stack there. Just a peek. Okay. And that's a 2.05. Let's see. And you guys, are you transmitting at 2? Okay, so if you stop your transmitter and try transmitting at 2.0. Oh, sorry, you guys do. Yeah, if you flip over to 2, do you get.
You're already at 2.
You're already at 2?
You're getting something now.
Alright. Try turning the transmitter on at 2 gigahertz. I would make such a bad FCC official. It's a bit messy. So now you can turn on that uplink as well. Yeah, let's just see what. So the UE. If you come over to the left-hand side of the screen, try and turn on the transmit. Okay. You guys kind of get the same as well. Alright, so we have some successful links back here, but no proper data throughput just yet. Alright, I'm gonna, yep. Yeah, this will be leakage from some of the other channels. So which frequency is that? 1.95. Okay, cool. So we've got a couple of successful connections. We've got some weird frequency allocation stuff going on the other side of the room. So now if everyone can, you turn off the transmitter, turn off the receiver as well. And what I'll do now is, let's work together. Now we'll try and do an area-wide broadcast to everyone. So everybody close down the code. If it asks you to save, say do not save. And if everyone can open up all the tables, even you guys at the front here, if we can all open up that, oh, not the downlink, sorry. This mouse is bad. If you can open up that UE here and set it running. Of course, I have no hardware. And then just wait for that FPGA to be ready. Now let's set up a broadcast. Yeah. Oh, right. Sync cancel. And we just need to stop the code. So if we scroll that and over to the right, you can press the stop button there. Yeah, I should have pointed out to you guys as well. There's a stop button over on the right here. If you need to stop the code, you can press that. It's better than aborting the code, because aborting the code will leave some references open, which is normally okay, but sometimes it will cause you problems later. So use the stop button to stop the code when you can. And then what we'll try and do here, so yeah, if you open up the Eno beacon, and if we go to data at the top left, and reset panel to default, and now run this code. Cool. Let's just scroll across. FPGA is ready, so let's go over to the left, turn on the transmitter and the receiver. These frequencies are good. Okay, so if everyone now, if you turn on your downlink receiver, let's see what you get. So we're just using one base station now. Okay, the constellation comes through, it's a little bit messy.
Which process?
Just leave them as defaults. So if I look correctly here, host UE. So yeah, the receiver frequencies are up there. So 2 gigahertz receive and 1.8 transmit. So if you now turn the transmitter off. Did everyone just lose connection?
Yes.
Yeah.
Good. And then if you take that power, turn that to 30. and run it to the on again. How's that constellation? Okay. Cool. All right. So now what we'll do, we've set up the base station. Yep, I'll come around and just take a look. You can leave them as default for this one. Just run the code. So yeah, those ones look good. Yeah. And then if we look at their C. Okay. Let me see if the base station is still running. So if you got that one still running, so if you leave that one running, that's all good. This is the house. Yeah, this is the house. Yeah, that's Yep, that's correct. We're using the right hand side. I'm not sure why you see nothing. Come back here. Oh, you know when we change the frequency, we start to stop the receiver. So, yeah. So tick to off, and then tick on. There we go. Yeah, so for those frequency changes to take effect, what you have to do is just turn the transmitter or the receiver, whichever one you've made a frequency change to, you just have to turn it off and back on again. Because that carrier frequency is set by the local oscillator at runtime, so you just need to give it a chance to change. Okay, cool, but it's pretty messy, right? Alright, excellent. So, you know that stop button I told you about? We can all stop the code now. Yeah, you can stop the base station as well. So what we just managed to do then, we've gone from making multi-base station, multi-user connections. Now we set up one base station, and we just made a downlink connection and then an uplink connection back from everybody to this one base station. But you saw that constellation was pretty messy as well, though. So what we were doing now with these pieces of code is we've set up this LTE physical layer stack with a little bit of MAC on top, but we're only sending just pseudo-random ones and zeros, just a bit stream of rubbish, of noise. So wouldn't it be a bit more interesting if we could actually put an application on top? So I mentioned before about how we can do things like pair up LabVIEW with other environments. We can pair it up with things like NS3, or we can pair it up with other things. What I want to do is pair it up now with VLC Media Player. And we'll do that using UDP port. So if I should have drawn out a diagram beforehand. Are you ready? We'll do this on the fly. Microsoft Paint. So what we're going to do is we will, VLC is orange, isn't it? Let's choose this. So we're going to set up a VLC player and a second VLC player. And what that's going to do, if I create this here, this is going to talk down to LabVIEW. And then we have those boxes that, no, undo that. That's not what I want. And then we have as well the software-defined radio, right? So what we're going to do is set up a stack whereby the VLC player spits out the video stream to a UDP port. And then the LabVIEW looks at the UDP port to pick that up. And then it transfers it over PCI to the radio. The radio is going to transmit it. We're going to do this in loopback, just for the sake of time. Pick it back up over PCI to LabVIEW. LabVIEW is then going to decode that video information, put it out to a UDP port, where VLC is going to look for it and receive it. So we're making an entire end-to-end video downlink. So what we'll do is, back in this piece of code, if we use a little X, just to close everything down. Use the stop button to stop the code and then close it. What we'll do is we'll open up that last piece of code at the top. Can you see there the LTE host DL downlink? And as soon as you got the green run button, press run and get that running. And then go over to the right-hand side and look for that FPGA ready button. Anybody doesn't have FPGA ready? Okay, good stuff. Now what you can do is come back over to this view here. You can leave the frequencies as they are, and what we'll do is we'll try this and see if we get a lot of interference, and if we do, we'll spread out different frequencies. If you turn the transmitter on, you should see the frequency block come up. Turn the receiver on and you should see the constellation. Ah, yeah, that's a real mess. Yeah, that's because then your signal power is way higher than the rest of the room. All right, let's split up frequencies, guys. I thought it would be messy, but I didn't think it would be that messy. So remember to turn off the receiver and the transmitter. If you guys go for something like 1 gig, and we'll go around the room. If you guys go for like 1.1, 1.3, 1.4, and this is the same frequency on both transmit and receive because we're just doing loopback, right? So 1.5. All right, you're at the limit of the instrument at 2.2. I would recommend 1.6, 1.7, 1.8, 1.9, something like that. And remember to have that G in there. These are gigahertz we're talking about. If you put 1.9 in, it's going to change it to 1.9 hertz. Right, that's a lot cleaner. That is a lot cleaner. So you should get a really nice constellation plot here, like really neat, because the transmitter and receiver are right next to each other, and you should start to get a throughput graph here, and that graph should be almost entirely all green. Now what that means is that what we're doing here is we're just doing what we did before. We're transmitting just a pseudo-random stream of ones and zeros. The green on that graph is ones and zeros, just random noise data. If you start to see blue, that is user data, and that'll become important later. What this piece of code is configured to do is that if we're not using the entire downlink channel that we have described at the clock rate that we have described it, it will pad on to our user data just some random noise, just to make sure we're always using the full channel for ease of use. So, what I want you guys to do now is you should, if you go to the desktop, let me show you, you should find Application Frameworks Video Demo. I want you to open that up, and there's a folder in there, Video Demo, and there's a number of batch files here. What I want you guys to click on is this one. So Video Loopback LTE. If you double click that, we get another warning message, just say, yeah, allow access. You get 2 video files playing. So if you see mine, this one here this is the transmit video. That's that one on the left-hand side that we described first. There's no video playing because it's pushing it all to that UDP port. This is the received video. Now you guys should see video playing here, a National Instruments advertisement playing there. That is what this one is transmitting. So now prove to yourself that you are actually transmitting that video for real over the airwaves. If you take that right-hand antenna and unscrew it, what you should find is after about a second or two, that video stops playing. Now, unfortunately, it's a digital video. It's I think it's 2064 format or whatever. It's not like analog video where it goes to static. It has a buffer, a video buffer that it's writing to, and that's why it takes 1 or 2 seconds to stop, and then it just freezes on the last frame. So unfortunately, we don't get to see that cool degradation. It's still going, but it's all a bit broken. So that will primarily be leakage across the device to there. Yeah, you can pause the video as well. And if it's still playing for a second, but it actually didn't stop. You killed it. So we managed to get a tiny bit of video feed through here at the table at the end, just through leakage, just through that open port. Has anyone else seen that as well? Yeah, we all saw. Pretty good.
The one that's sending, the other one, very close.
And then what happens to the video? It keeps on going for a couple seconds. If I cover that port, this is our animation. Yeah. There we go, I'm just about getting it. Okay, so put that receive antenna back on. And your video stream should come back in full HD. Cool. If you, I'll take it. So this down here does the transmit and receive feedback. So I'll set this really on. This guy. So here's the other one. Turn around the room. So what you'll find is that the batch file that you opened that receive video VLC in always on top mode. So you can't get rid of it by clicking around it. What you can do is you can minimize it, but my recommendation is just to move it to the side of the screen so it's halfway off the screen and you can at least see some of LabVIEW. Now what I want you to do is head back to these graphs that we talked about. What you should see is on your data usage graph is that yes, you still have a lot of green bandwidth, but you should have some blue bandwidth as well. Now that is your video data. That's how much of this 40 megahertz, or I think it's actually a 20 megahertz channel within a 40 megahertz band that we're actually using. Is there a tiny bit of blue? Tiny bit of blue for HD video. Okay, so now let's start playing around with that channel. What you'll see is that you have a characteristic shape on your transmit that you should be able to see on the receive as well. It's like the full LTE band, but there's a notch out of one side. Now what that is that we have decided not to use the two first resource blocks, those two subcarriers right at the start of the band. Let's mess around with that a little bit more. Take note of what number you have here in your throughput. That is your total data throughput, video and random noise for the whole channel. If you come over to the transmitter here, what you'll see is that there's this resource block allocation. And you see we've chosen not to use the first two subcarriers. Let's knock out a couple more. So if you click in the middle of there, and if you say delete 1, 2, 3, 4, 5 ones, put in 1, 2, 3, 4, 5 zeros, anywhere you like, any number, just make sure you get the correct number in total. And then click outside of there. What you should see back over on your transmit and your receive are those resource blocks are now missing. There's not even a carrier inside them. Now, I mentioned GFDMA at the start of the session. What we were doing with Gerhard Fettweiss on these devices with GFDMA is we were knocking out some of the non-essential resource blocks in the middle of an LTE band and putting the very narrow GFDMA spectrum inside those missing resource blocks, that actually allowed GFDM and OFDM to coexist together inside the same channel, which was pretty cool. What you'll see if you scroll over to that data throughput is you should see for now a notch where your data throughput has gone down. And if you look at the number of throughput, that should be a lower number of megabits per second in total. Does anyone not see that? Okay, cool. And then lastly, what you can do is come back over to the left-hand side here and turn off the transmitter so that it goes off. And then go back to that video. Hopefully you've still got it in front of you. The video should last 1 or 2 seconds and stop. Should freeze on like the final frame that it has a valid transmission for. Go back to the transmitter and turn it on. Turn the transmitter back on. And what you should see is that video picks back up as soon as the video button is full. And you'll notice it doesn't pick back up from where it left off. It picks back up at the most recent transmission. So the advert is actually skipped a few seconds forwards so that you're always viewing live data. Okay. Is everyone happy? All right, excellent. So again, at the top of the screen on the right-hand side, you can use the stop button to stop this code. And then what we'll do is, I need to grab some water. If anyone else needs to grab some water, do it now. And we'll run 2 more exercises after this as well. But for now, we're done with the LTE stack. So let's leave all of that LTE stack behind. Let's go right down to the physical layer. We'll talk just about OFDM, not so much about LTE now. And what I want to show you is how do you use this hardware and software in order to do algorithm prototyping and design. So I'll show you the first one up here on the stage. You guys can follow along, but I'll do it quite quickly. If you close all of VLC, so just close all the windows, stop the code running, and then what you want to do is come here, File, Close, Project, there, and you can say, don't save. No need to save anything. You should get back here. So File, Close, Close Project. And now what I'll do is I'll take us over to the learning section that I said we'd use. And before we really... No, let's go into getting started. So inside of here, what I'll show you is just... Actually, yeah, let's go to the examples. I'll show you a completed one just for the sake of time. No need to follow me here. I'll just show it for 2 minutes. You can see we have all these different completed examples for different basic modulation schemes. What I want to show you is the ability to program in whatever computation method works for you and your particular project. So at the moment, we've been programming primarily in LabVIEW, which is all of these function blocks with the wires that travel between them. I'll show you a couple of different ones now. The first one I want to show you is that there's always, with programming languages, there's always 100 ways to do any one task. Now what we're doing is FM demodulation. Over on the left-hand side, I find the USRP. Here I do FM demodulation on the signal that I read out of this block. Then I resample it, send it to the sound card of the PC, and play the radio station that I'm trying to listen to. What you see there is that inside a LabVIEW, there's an FM block. Right? This is about that inbuilt IP that's already in the software. So for FM demodulation, there's a block. This is good if you want to just test ideas quickly, because you can take that block away, go put the AM block in. Take it away, go and put the QAM block in. It takes like 3 clicks just to change what modulation or demodulation you're doing. So it's really quick to take an idea and just test it out. You don't have to necessarily consider whether it would really work. You can just try it. Makes for some very lazy programming, which I quite like. Sorry? Oh, it's demodulating FM signals, I think. Or maybe it's just called FM demodulation. It should be in the modulation folder. Now, if I show you, you can actually do things a different way as well. You can use those LabVIEW functions but you can do the algorithm yourself. So if you don't like our FM demodulation algorithm, that's okay. You can build one up. So what we do here, this is the unwrap phase function in LabVIEW. So we get the phase. So this is the complex coming in. You've got real and imaginary coming out. Take that phase, unwrap it, and then we do a differentiation. That's a differentiation block. And that's all there really is to FM demodulation. Or, if you want, there's another way to do the same thing. So here we use .m syntax. Now, almost all of us have got some existing IP in .m, some existing project or code, or you go online, you go Googling to try and get some help, and somebody else has done it, but it's for a different environment. You can bring your .m in here. This is a full debug and deploy, so if you want, you can create your .m in there, and it has all of the usual functions, drop-down suggestions for syntax and error checking and all that kind of thing. If you want, you can import and export .n files as well, so you don't actually have to copy and paste every time. And there's this block for .m, and you can see it's all the same. It's all the same. We find the angle of our samples. We then unwrap the angle, and then we just find the FM demodulation product by differentiating the unwrapped angle. It's exactly the same as what we did before. There's also here inside of, oops, sorry. Let me see, where are my models of computation there, sorry. There's also a block for C. So you could do exactly the same in C programming if that works for you, or if you have existing IP in C. So what I'll do is I'm going to just close that project without running it for the sake of time. What I want to do is show you how we do all of this on the FPGA, not just high level at the host. So if we come back here, let's go to getting started, and everyone can follow along now. So we're on learning and we're on learn, not examples, and we go getting started. And then let's go into overview of FPGA design flow, that middle one. And for the sake of time, we'll dive in on lesson number 2. So let's go into algorithm design and testing. So if you click that, you click on create. And what you get is, Clippy. This is the lesson here. This teaches you how to use the environment. You can go through this in your own time. You can click through and it teaches you exactly what to go and do. All of this is hyperlinked. It's HTTP coding inside of here. So if you were to click on a certain part of this, it can actually operate the environment behind it for you as well. Sorry, I said HTTP, I meant HTML. So I'm just going to minimize, no, actually, let's keep that pane open for the time being. What we have open here is a test bench. I'll ignore that for now. And what I'll do is I'll double click, can you see my OFDM TX? You want to get rid of Clippy, get rid of the lesson. Come here, and it's actually going to try and teach you how to use the thing. Just say, don't worry, say, okay, I got it. Just leave me alone, get rid of the tips. And you should have here what's called a multi-rate diagram. Now, how many people in the room have ever used GNU Radio? Yeah? 4, 5, 6? Okay. And, I mean, how many more people know of GNU Radio? Have heard of it? So GNU Radio is that open source software that I described before for programming these radios. This multi-rate diagram will look very similar to what you'll be used to from GNU Radio Companion, which is the graphical way of working with GNU Radio. So what I want to do then is we'll follow through on a couple of instructions here. Let me just get to my page. There we go. So what we'll do now is if we come here, what we want to do is put into action an OFDM algorithm. And the start of any algorithm is going to be some kind of stream of data. So what we can do is, over here on the left-hand side, you see stream manipulation. And we want to bring in a stream constant. We're not going to have a stream input. We'll just have a stream constant because we're not going to change that stream of data. This is actually going to be pilot data that we'll put in. If you click on stream constant and drop it down, it should look like this. And then over here on the configuration pane, just like you're used to in like normal Windows or Microsoft tools, you can configure everything about what you have selected. And what I want you guys to do is just change the numeric data type to a fixed point. Because we're talking about using FPGA here, we can't use a floating point data type on FPGA. So we'll use fixed point. And then what you'll see is you get the fixed point configurator. Now, we'll just keep it super simple. So let's put the precision of our fixed point just integer, just 1.0. Because we're only going to be working with ones and zeros in this data stream. And then say apply. And now it should look like this, and it should say fixed point, precision 1.0. Everyone up to speed? Cool. Now I could go into here and type out all the ones and zeros that I want in the correct order, but that would be really painful. So actually what I want to do is import an existing list of ones and zeros. I'm going to import some existing OFDM training data. So if I come over here, can you see down on the bottom right data source? I can change that to CSV, and then I get a little drop down, and it's already found my file because I put it in the right place ahead of time for you guys. And if you click on that, do you see there this changes? If you click on the edge of it, I appreciate it's quite hard, just click on the very edge. You can move this around. We'll drop that right there. And what you'll find is this is a long stream of, hopefully for you guys, all ones and zeros. I've got all zeros. What have you guys got? All zeros as well. Why did I have ones and zeros earlier? Let me just double check I've got the precision right on this, because it's picked them all up as ones and zeros. That's correct, that's correct. Has anyone got anything different from all zeros? All zeros? All right. We shall proceed, and we shall see what happens with our training data. It's not going to be very good at training a system if it's all zeros. Let's see. So we'll drop that down, and then the next thing we want to do is we want to take this stream of data, and we want to map it to a constellation in order to go from bits of data to actual symbols on a constellation plot. So what I'll show you how to do is, instead of navigating all these menus down on the left-hand side, all these different function blocks, you can just search. There's a shortcut to search, Control and space. Can you see the search box at the top there opens up for me? And what I want you guys to do is type in numeric and then constant. You can just put numeric CON and you'll see numeric constant there. And your mouse now has a numeric constant. So let's put that down here. Just place it down. We can click inside and say leave this as how accurate to be. Let's go for 0.707. Do you guys recognize that number from a Quam constellation? Right, we'll come around to that again. Now what you can do is, I want you to duplicate this. There's a couple ways to do it. You can drag over, select it or click it to have it selected. Control-C, Control-V, like you would in Windows. Or like you would in Word or PowerPoint, you can hold down Control, click and drag a second copy away. Or you can go and create an entirely new one. Put this one just below, and what I want you to do is make that one, just click inside, change the value, and make it negative 0.707. Now what we want to do is actually map the data. So what I'll do, again, I'm going to use Control Space, and I want to find equal to 0. You see that function there, equal to 0? If you type just the word equal, it should come up. Click that, drop that in front of there, and then if you hover over the edge, you'll get this wiring tool. I want you to wire the two together. So what that's done is it's changed our fixed point data type into a Boolean data type. Now I have trues and falses instead of ones and zeros. It's the same data, it's a different data type that we can work with in the next stage. Slow me down if I'm going too fast. So control space one last time, and what I'm going to do is type in select. Now select is like a really lazy function. This is an easy way of doing an if-else statement. So drop down your select, and you see it has 3 inputs on the left-hand side. Wire in this less than 0 into the middle. Wire up this 0.7 into the top, and at the bottom, wire in negative 7.7. What we've done is we've just programmed in LabVIEW an if-else statement that says, if 1, create value 0.7. If 0, create value negative 0.7. All right, so let's carry on going then. So what we want to do now is now that we have mapped, this is our input bit stream of pilot data, and we've mapped it to this. This is our constellation map, essentially. We've mapped the two together. What we want to do now is actually build a packet. So I'll take you through the design stages for that piece by piece. So the first thing we're going to do is we need to break up this long stream of symbols into IQ data. You remember I said the radios receive IQ data and transmit that IQ data. So we need to get from symbols to IQ. That's pretty easy for us to do in this environment. If you guys come back here to this stream manipulation palette, what we want is this one up at the top, distribute stream. Can you see the symbol? It's 1 in, 2 out. If I click on that and drop it down, what I want to do is I actually want to wire in the very top. No. Should stop using the trackpad. Wire it into the top there. What that's going to do is it's going to take each symbol and it's going to split into 2 data streams, an I data stream and a Q data stream. And we're actually then, the next stage that we're going to do, it sounds wild, but we're going to recombine the data streams. But we're going to recombine them into a different data type. So all of this is like data type manipulation that we're doing in order to get from our high level down to hardware. Sorry, go on.
Doing one symbol and then the other one, like reading one, and the other one around as leaving.
So what we have back here is that each of these bits are being put together into 2-bit symbols, and then we're splitting the symbol out into a different. It's like going from, say, Cartesian into more of like a polar or a different way of describing the same data.
We have half the speed.
Not quite, because we'll receive those same symbols at the other end. It's a really good question. Within the algorithm, there's a time at which the data is running at half pace. That's a fantastic point I want to come back to in 5 minutes. But from a downlink point of view, we transmit the symbols and we don't lose the data rate. And then at the other end, we break those symbols out into 2 bits. So it's as though our data rate doubles again at the other end, so we never actually lose it. But really good point about the sampling. And that's the whole point of why we're doing this in multi-rate diagram. So we're going to come on to it in 5 minutes. So one last thing that I want you to search for, is probably not the last thing, I keep on saying that, is if you type in real and imaginary, can you see that top one that comes up? Drop that down and wire the top one into the top one there and the bottom one into the bottom one there. That's really ugly, but we'll leave it like that for now. So let me walk you through what we did again. We got ones and zero numeric data. Then we went to Boolean. Now we're back in double precision. But that's okay because we've got symbols at this point. We had bits and now we've got symbols. Now we're getting I and Q. But just to make it easy to talk to the instrument, we're not going to send I and Q as two separate data streams that could get out of time. We're going to combine them into complex numbers. So this is going to be, you know, like 0.7 plus or minus J 0.7, something like that. So then we keep I and Q aligned together within the same data type. And we're almost there. What we're going to need to do now, if I just make sure I follow this through correctly, we are creating that training sequence, or pilot bit, if you like, and we haven't defined any user data. So now what we want to do is take all of this and then copy it and paste it down here as well. So you get a duplicate copy. But what we're going to do is, you see the data input, I'm actually going to delete that. So I highlighted over it, I clicked it, and then I pressed the delete key on the keyboard. And what we want to do is actually, if you remember from earlier, we have this input. We want to put input in. But hang on, we got a data problem again. So input, if you click on it, can you see it's an unsigned 32-bit integer? That's not going to be compatible here. So what we need to do is just disaggregate that data. So that's another function inside of here, inside of the stream. Oh no, actually, I think it lives in one of the other palettes. Disaggregate. If you want to know where any of the functions that you're searching live for future reference, you can click on Show in Palette here on the right-hand side. And if you click that, it brings up where that function lives. And what we're going to do is just, inside of here, instead of output chunks 2, let's put that into output chunks 32. You can see that creates a constant on the diagram for us. And then we can wire it up like that. Now the last thing we need to do, does anyone know how many pilot bits are supposed to be sent for every piece of user data in the OFDM standard? 10 total. So I didn't know this. I had to look it up as well. So for every 5 pieces of user data, every 5 user data bits in OFDM, you're supposed to send 1 pilot bit at the start. That's how you create an entire OFDM packet, if you like. So what we do over on the right-hand side is we just bring up one more function, which is this interleave stream. We can place that down, and then we can wire in our 2 streams. And there's no need to define these because we can do that through configuration. So we can leave input stream 0 at the top. That's the pilot bit, so you just leave that at 1. That's all we want. And if you put this up to 5, you can see it creates a constant. So what this will do now is for every 1 pilot bit, it'll take 5 user data bits. Now, coming back to the question on sample rate, if you wanted to do this in normal LabVIEW or in C or in a different language, you would have had to have used loops. That's because in normal LabVIEW, every time, say, one function block runs, it waits until all of its input data is ready, and then it outputs all of its output data. You would have had to have put that in a loop. So we would have had to have had some weird loop structure that ran the top code once, then the bottom code 5 times, then went back to run the top code once, the bottom code 5 times. Up here, you can change what you're viewing. If you click on that at the top right and put sample counts on, you get the whole screen's covered in little numbers. And what you'll see is that for every time the user inputs a single value, that creates 32 bits. That makes sense, right? Because they're inputting a 32-bit value. Every time we do this disaggregate, we're trying to create I and Q, we have to wait for 2, just like you said, 2 of those symbols before we can define I and Q here. For every 1 time this piece of code runs at the top, the bottom piece of code runs 5 times. And you can view that through the number of iteration counters on those samples. All of this, whilst you are designing that algorithm, has all been done for you under the hood by LabVIEW. So you never had to implement all that crazy, like computer science nested loop disaster stuff yourself that gets really hard to debug. So we're not going to be able to finish this one entirely, but that's okay because we gave you a solution file. So if you open up the solution folder on the left and double click that piece of code, you can see here, this is the solution file where we finally finish off the whole thing. And what you can do is you can run this and you can see the output. So this is the graph. This is the little probe that we put in before the FFT. You can see that we get, I think it's 8. Yeah, 8 total packets of OFDM with that characteristic divider right in the middle of the packet. And then you can see that after the OFDM, we're fairly randomly distributed. So we've padded the rest with just pseudo-random noise or 1s and 0s for I and Q. So what I'll do now is I'll try and just squeeze in the last exercise and then maybe leave a little bit of time for conversation as well. So back to our favorite button, File, Close, and then go Close Project. It'll ask if you want to save. Just say no. No need to save. And what we'll do is you get back to the Learning screen on the Learn tab. Let's go into Getting Started. Overview of the FPGA design flow. This time I want to show you one really cool feature inside this software, which is the fixed point conversion. Has anyone ever converted a communications algorithm to fixed point to run on FPGA? Sorry? Yeah, that kind of thing. So when you create your algorithm in MATLAB, and then you test it out in Simulink, and then you say, maybe you use like the HDL coder or something, or like, sorry. Yeah, exactly that. And you have to take all of the constants and all of the multiplications and stuff that you have inside that algorithm. Hopefully you haven't got any divisions because they go really badly in fixed point. And you have to convert them all over in order to deploy to the FPGA. Well, when I did that in my degree in about 2010, we couldn't use the HDL coder, which takes your algorithm and converts it to HDL for you, because we were coming up against too many compilation errors. So we had to go a manual route. We actually downloaded huge Excel spreadsheets of floating point to fixed point conversion. There were multiple columns, and you had to look up what floating point number you had, and in different precisions, what fixed point representation that number actually was. And it took hours. Luckily, we piled all that on the PhD guy, but he had to go through and literally stare at these Excel spreadsheets for days on end. Well, what we've got is a tool built into the software that can do that for you. So if you click on this and then click Create, it'll do that same process. It goes away. It's going to create all this code. You can close the wizard. Just get rid of that. And then what we want to do is, shall we start from here? Shall we do this? Let me see. No, so this is, you'll recognize this, right? This is the algorithm that you were just designing. So this is a completed version. Let's not mess around with this for the sake of time. So we can close that for now. Open up the test bench here. Now what we're going to do is, can you see you got the panel? This is the user interface of the code, and you got the diagram. Click on the diagram, and let's do some coding behind the scenes here. So right now you have a test bench. So you can see on the left-hand side, it generates a random bit stream, puts it into the file we want to test, does a comparison. At the moment, it's just doing like an autocorrelation with itself because it's only got one thing to test, and then it gives you the results of the test and tells you how good the algorithm was at converting that pseudo-random stream of bits. What we're going to do is we're going to take that solution and we're going to duplicate it because we want to go mess with it. Right now, all this is running up on the laptop, so all of this is floating point stuff, and we want to try and make an FPGA version. And what we want to see is the difference between our FPGA implementation and our desired real algorithm that we've been developing high level on Windows. So what you can do, if you click on that block in the middle and then come up here to edit, I want you to click on duplicate hierarchy from selection. You'll get this window. Just name it, I don't know, what should we name it? Just like FXP, so fixed point copy, will do absolutely fine. And then press duplicate and place on diagram. Do you see how I have it now selected? I want you to drop it in right underneath there. And what we're going to do is where that input that says input, I want you to wire that up to the same bit stream here so that we are doing a valid comparison. Then you can click on this wire. You see how I have that wire selected here? Click on that wire, hit the delete key to get rid of that. And into our comparison then, I want you to wire the output. So you see the code as I have it now. So now what we're doing, our test bench is generating the same data set for both algorithms. It's putting it in, and then we're getting the output from both algorithms, and we do a comparison. So come back now to the panel and press run. You see the little green run button? Mm-hmm. And now the mean squared error in dBs is that difference. That's the result, right? That's the result between these two algorithms. And it says minus infinity, or may say plus infinity on your screens. Why does it say infinity? Any ideas? There's no error, there's no difference, because we didn't change anything about the algorithm, right? We just duplicated it, so we're still comparing it with itself. So let's go back to diagram. Let's go make changes to this now then. So what I want you to do is if we click on this, we're going to have to do a little bit of manipulation. I can't click that yet. Why can't I click that? What do I need to unlock? I think we might need to just save this. So if you go to File, say Save All, and just press Save. Yeah, that was it. I couldn't go changing the algorithm before I'd saved the project, which is actually a nice little safety feature before I go messing with my algorithm. But luckily we're messing with a copy of it. So after you've pressed Save and you've gone through that, click on this bottom box, and can you see in the configuration pane over on the right hand side here, you have Profile Fixed Point Data. So I want you to click on Profile Fixed Point Data, and does everybody get this at the bottom? So this is a little profiling tool down here, and what this is going to do is it's going to make suggestions about the perfect, if possible, perfect fixed point values to use in order to get an excellent copy of the algorithm that will work on an FPGA. But you can see all of the results, all of its suggestions that it's going to make down here, for all the different constants it's found within that code, say run required. It hasn't had a chance to run the code in the profiling tool, so at the top here, just press run. And now what you see is for every different constant that it's found, it's made suggestions on exactly what precision and what fixed point data type to use. And it's real easy for these numeric constants. Remember, those are those numbers we were putting in, 0.7, minus 0.7, all that kind of thing. That's easy. What's difficult to represent on an FPGA is an FFT. That's really where this whole algorithm's quality is going to hinge on if we want to try and make a working prototype. So what we're going to do now is we're going to mess around with that number. Now, it made this suggestion to use an 11-bit fixed point, negative 2.13 precision, and it thinks that the SNR, so the dB difference between the perfect algorithm and the resulting algorithm, will be about 50 dBs, 50.6 dBs. So let's go and actually test that out now. So if we navigate back here to the panel, what we can do is actually run a test of that. So come down here and click over on one of these file names. And then using a super common Windows command, if you go Control A, it'll select all. Does everyone get this view? All right, great. Now what we're going to do is we're going to say, okay, thanks very much for your suggestion. Please implement the suggestion you have made. Now it will implement the recommended suggestions based on what you have here in strategy. So we are going for a strategy where we prioritize the signal to noise ratio of this algorithm. So we'll leave that on SNR and then press this button over on the left, convert using suggestion. That should just take a second to do the conversion. And now what we can do is run the code again. Aha, it's compiling. And then once it's done with the code, you all should see a value about negative 55 dB SNR on the difference between those algorithms. So which is a great success, right? That's a significant chunk of SNR. We haven't impacted the algorithm. We could now that we're 5 dBs beyond our target of 50 dBs, we could just, give up and call it a day. Package that up and go and build our prototype. We know our values now, but that's often not the case. So more often than not, you actually want to do some slight tweaks. Maybe you want to improve the number. Maybe you did not meet the desired value that you were going for. So what we can do now is actually go inside each of these values and make individual changes as we go on. So what we'll do now is if we click on, say, if we go back to the diagram, we can open up this here piece of code, and over on the FFT, if you double click that block, open up the FFT, and then click on it, you can see here the suggested precision that it's said to use. Now if you click inside there, what we could do is we could tweak that away from the suggestion to get a value that maybe suits our algorithm a little bit better. So let's make just a tiny change is needed in order to swing this algorithm one way or the other. So if you click inside there and change that over to negative 2.12, click outside of here, can you see that we've got this little asterisk at the top? That's just telling us we've got changes that need to be saved on our code. So go up here to File, Save All, and then the little asterisk should go away. And now we've changed our algorithm, fixed point implementation. So we'll go back into here, and I want you to navigate to the panel on the test bench, and we're going to compare those two algorithms again. So remember, our previous value with the perfect suggestions was negative 55. We went and made a very small tweak. If we run that again, you should see a new value of negative 50. So that's actually not as good. So we made a bad change. But I'm just showing you how you can tweak the algorithm a little bit in order to get a slightly better value. Now the next step after this would be if you came to, say, close that project down, go to File, Close Project. We were in Getting Started, an overview here. We skipped the very introduction. We did steps 2 and steps 3 of creating an algorithm that could run on an FPGA. Now what we need to do is actually deploy the application down to FPGA. I'm going to stop here because we've got just 10 minutes left. I'm not going to go and do that. One of the big reasons I'm not going to go and do that is that FPGA compilation takes time. So this is a very small algorithm. It would probably just take 7 or 8 minutes to compile, maybe another 7 or 8 minutes to set up that compile. But if you've got a large, say an entire LTE stack, you could be talking about compilation times, depending on what you compile on, anywhere from 30 minutes to 8 hours. If you're on like a little Diddy i3 laptop or something like that. A lot of people use a compile farm or a compile server. So NI tools are automatically hooked up to Amazon. It might be Azure servers now. You can send off your FPGA code to the cloud and it'll compile like 10 times faster on a supercomputer somewhere in the continental US and then get the bit file mailed back to you ready to use on the FPGA. So at that point I'll stop. There's a huge amount of stuff inside of here in Learn and Examples. There's all these lessons that you can go through, some of them with hardware, some of them without hardware. LabVIEW Communications is something you can get off the ni.com website. You can get an evaluation period for like 45 days completely for free. Or, as most of you are at universities, they'll have the National Instrument Site License. You probably already have full access to LabVIEW. You just maybe not be aware of it. So talk to your IT guys, see if they have a site license covering the institution already, because you probably already have full access to all the software. If you can't get through your IT guys, just give us a call and we'll look up your university in our records and let you know if you already have the software on site or not. And then it's just a case of downloading and putting in the serial number. So all of that aside, we went through, just to recap, the LTE stack that's built into the environment. There's another one for ATEM 2.11 as well, and like we said, for massive MIMO and soon millimeter wave. And we managed to do that point-to-point connection, then we did a broadcast to multiple UEs, then we did a loopback with the video transmit on top. Now what we've done is we've created an OFDM algorithm in a multi-rate diagram, saved us doing some crazy nested loop structures. Then we changed that algorithm over to fixed point, and it's now ready to be deployed on an FPGA after a little bit of compiling. So without further ado then, I open the floor to questions. I realized that was breakneck speed. This is normally something I do in a 3-hour session, not 2 hours. So thanks everyone for keeping up. You all did a great job. We didn't lose anyone along the way, I don't think. Are there any questions you guys want to fire at me right now? Is anyone going to be using this when they get back? Or use it? We had a couple of examples. You guys using the X310? Yeah. So the X310 is the ETUS name for the exact same hardware that you have in front of you. Yeah, these are X310s. Yeah, we just put a different sticker on the front. Is anyone going to be using USRPs, GNU Radio, LabVIEW? Yeah, 1, 2, 3, 4, 5. So you've probably got an engineer who is in your area, wherever you are from the world. We have them absolutely everywhere. If you want to explore more of this, or if you need help as you go along, make sure to get in touch with us. I used to be working in an academic research lab as well, just for a few months, and it's very stereotypical of us academics to suffer in silence because that's what we're used to doing. Please don't do that with our equipment. Please call us, and we'd be absolutely happy to help you through whatever it is that you might be stuck on or trying to do with the stuff. Cool. So thank you.